Assalamu alaikum. Dear learners, in this video I am going to explain the ABCs of fiber optics. Fiber optic cable is nothing but a fiber that can carry light signal in it. This fiber can come from a number of materials that I will explain in this video. But before routing the light signal in a fiber optic cable, you need to have the complete setup. That is, you need a transducer that will generate the light. The light will enter the fiber optic cable through some mechanism. Then the light will move in the fiber optic cable and at the other end, some transducer will receive that light and will convert it back into the voltage or current signal. Therefore, these three things are the basic components of a fiber optic transmission medium. Starting with the transmitter, it is usually a simple LED because LED has a linear relationship between the input current and the output light. So we can easily control the light emitted by the LED by controlling the current through it. Therefore, if we have an electrical signal in form of a current, then that can easily be converted into a light signal which can later on be routed in the fiber optic cable. However, not any LED can work equally good. We will see in a bit that each fiber optic cable has different characteristics depending on its material and some other construction properties. These characteristics will dictate that what kind of visible light can travel through it most easily. Apart from characteristics of fiber optic cable, another very important characteristic that control the overall efficiency of the signal transmission is the proportion of power emitted by the LED coupled into the fiber optic cable. This means that how much power generated by the LED is in fact entering the fiber optic cable. You must have seen an LED and you know that when it glows, it throws light in every direction. But in case of fiber optic cables, we don't want light to go anywhere else except the fiber optic cable. So we have to make special arrangements so that the light generated by the LED enters the fiber optic cable as much as possible. This graph shows that what is the relationship between the misalignment of the LED to the power that is entering the fiber optic. In the first case, if the fiber diameter is much lesser than the beam diameter that is generated by the LED, then of course the complete beam cannot enter the fiber optic cable. Therefore, in such case, a low proportion of power will enter the fiber optic cable. And if there is a minor misalignment, then the whole power would be lost because no portion of the beam will enter the fiber optic cable. In the second case, the fiber diameter might be equal to the beam diameter. In such a case, if there is perfect alignment, then complete power will enter into the fiber, whereas if there is a misalignment, reduced power will enter the fiber optic cable. In the last case, if the beam diameter is much less than the fiber diameter, then a bit of misalignment will not cause any problem. The whole beam generated by the LED can still enter the fiber optic cable because the fiber optic cable has a quite wide diameter. Making a smaller diameter fiber is not that much of a problem, but making an even smaller LED surely is. On the other hand, the fiber optic receiver is a device that receives the light signal and converts it into an electrical signal. This can be easily achieved by using a pin diode or a phototransistor. Depending on the light beam used, the choice of the receiver can vary. For example, phototransistors provide a good sensitivity but quite low bandwidth. Therefore, it can only be used with a specific frequency light only. On the contrary, the performance of the pin diode is quite opposite. It has lower sensitivity, whereas it can cater large range of visible light frequencies. However, if both characteristics are desired, then sometimes avalanche photodiodes are used as receivers in the fiber optic cable transmission, but at a cost penalty. This was everything about the transmitters and receivers of the fiber optic cable transmission system that I have to say. Now let's look at the main component of the fiber optic cable transmission system, that is the fiber optic cable itself. Firstly, I'm going to discuss the main structure of the fiber optic cable. From the outer side, the fiber optic cable looks like just any other cable, but from the inside, it is totally different cable. The main magic is happening at the center of the cable, whereas the outer covering or the jacket and the coating around the inner portion is just to protect the cable from damages. Right at the center, we have a core that is surrounded by a cladding. These two portions of the cable are responsible for routing the light from one end to the other end. The light travels inside the core, and if it tries to escape, the cladding portion will reflect that light back into the core. This thing is achieved by the difference in refractive index of the two materials that are used to make the core and the cladding. The phenomena of total internal reflection is utilized over here. You might know from your physics class that the light will completely return back to the first material or the first medium depending on two things. One, on the difference of refractive index between the two mediums, and secondly, on the angle with which it approaches the second medium from the first one. In fiber optic cables, the refractive index of both the cladding and the core is controlled by choosing a suitable material, whereas the angle with which majority of the light beam moves is controlled by the alignment of the transmitter LED. Mostly there are three different types of fiber optic cables, and the type is dependent on the material that is used to make the core and the cladding. In one type, both the core and the cladding is made out of glass, whereas in another, the core is made out of glass whereas the cladding is made out of a plastic. And in the last one, both the core and cladding is made of plastic. Moreover, if we look closely and critically, then the amount of light escaping from the core also depends on the wavelength of the light that is being used for a particular pair of core and cladding material. However, this relationship of the amount of light escaping with the wavelength is quite nonlinear. That is, for some wavelength, attenuation might be larger, whereas for the other, it might be lesser. In the data sheets, only the most favorable wavelength is mentioned. That is, the wavelength for which the attenuation would be minimum. Therefore, you can still use some other wavelength, but at a degraded performance. Although total internal reflection is ensured during the construction of fiber optic cable, but still there are certain other causes that causes the attenuation of the light which is traveling in the core. There are three major ways that I am going to discuss that causes this attenuation. The first one is called Rayleigh scattering. You must have seen a mirage on a hot summer day. If the air near the Earth's surface heats up at a temperature greater than a particular value, then its refractive index is changed so much that it causes the light from the sun to totally reflect back. This causes you to see a water-like effect at a distance. This is because the angle from which you are seeing that surface, at that angle the light is not able to touch the Earth's surface and is being totally reflected due to total internal reflection. This thing can be seen through our naked eyes, especially in summers when the temperature of the air has risen a lot. However, this phenomena is always there. Additionally, you also know that whenever refraction occurs, small portion of light always gets reflected back. I can safely say this thing that whenever there is a refraction, there is always total internal reflection as well. However, it depends on certain things that which phenomena is greater than the other. So as light travels into our atmosphere, due to microscopic changes of refractive index between different layers of our atmosphere, total internal reflection, no matter how much negligible it is happening in the atmosphere. This kind of scattering is dependent on the wavelength of the frequency of the light. Therefore, this is one way of nature to protect us from high frequency X-rays, ultraviolet, gamma rays, and other types of harmful radiations coming from the outer space into our atmosphere. The lesser the frequency or the greater the wavelength, the less Rayleigh scattering will occur. From this information, you might have guessed that why the sky is blue. In the visible light spectrum, the blue or the violet light has the highest frequency. Therefore, it gets scattered the most while the light is traveling through our atmosphere. Therefore, the whole sky looks blue. Moreover, you can also appreciate that the longer the light travels through the atmosphere, the more scattering will occur. Therefore, if you go on a huge mountain, you will have high ultraviolet index over there. because the light has traveled through a less amount of atmosphere before reaching you. So there are more ultraviolet and blue light frequency components present in the light. As far as modern fiber optic cables are concerned, relay scattering amounts for up to 90% of the losses that are experienced in this kind of communication channel. This is because of microscopic changes in the core material that is quite difficult to control. The price of generating a very evenly distributed refractive index glass fiber is too high. The other case of attenuation of light signal traveling in the fiber optic cable is of absorption. Although this case is still present but has been reduced quite a lot thanks to the advances in manufacturing technologies of the fiber optic cable. The absorption mainly occurs because of mostly water particles that are induced in the material during the manufacturing of the fiber. Nevertheless, the advances in manufacturing methods have overcome this problem to a reasonable extent, but it is still there at some level. The last cause of attenuation is not something related to the manufacturing of the fiber optic cable, but how it is installed in the overall system. As you know that the total internal reflection is dependent on the angle at which the light hits the cladding while traveling in the core. So if this angle is changed because of the physical bending of the wire, then the light will escape through the cladding because of the change in the angle. Now let us talk about how light travels inside the fiber optic cable and what are the principles related to that. Whenever light is guided down a fiber optic cable, at every reflection there is going to be a phase shift. You can imagine that thing by considering a sine wave colliding with a wall and reflecting back. Its phase is going to change. Now, depending on the phase change, the reflected wave might constructively interfere with the incoming wave or destructively interfere. Similar thing is happening in the fiber optic cable as well. The phase shift makes two different reflected beams to interfere either constructively or destructively. If there are multiple rays of light moving in a fiber optic cable, then each ray will most probably hit the cladding material at different angle and hence will have a different phase shift. If these rays after phase shift destructively interfere with each other, then they both won't be able to reach the other end. Whereas if this interference is constructive, then both waves will reach the other end. For a fiber optic cable, there are only finite discrete number of paths that produce constructive interference between the light rays. That is, if light follows those paths, only then constructive interference will occur, otherwise destructive interference will destroy the light rays. These paths are called modes of the fiber optic cable. Moreover, each mode has a different route from the start till the end and hence a different distance. Therefore, light traveling in different modes will reach the other end at different times. Only the zero mode is the path that is straight from the start till the end and is the shortest path. Ideally, there are no reflection in the zero mode path. How many modes can travel in a fiber optic cable is determined by the wavelength of the light that is used, the diameter, and the refractive index of the core. Because of the different modes the light travels in, different rays present in a beam of light will reach the other end at different times, although they started traveling at the same time. This is called dispersion. If you start the transmission of a beam of light at a particular time, then the zero mode will reach the other end first, and then later on the light from other modes will reach. We can say that the light pulses that are traveling through the fiber optic cable have been lengthened or broadened in time. This broadening puts a limit to the speed of data transfer or the light signal transfer that a particular fiber optic cable can support. Just for example, if you transmit a light at a particular time and at the other end the zero mode and the all other modes are displaced by 1 microsecond, then you cannot send the next signal earlier than that. Because if you do, then the slow moving modes of the first signal will overlap with the zero mode of the next signal. The dispersion we just talked about can formally be defined to occur due to three main reasons. Let me talk about each reason separately. The first one is chromatic dispersion. Electromagnetic waves of different wavelengths travel at minutely different velocities down the fiber. Therefore, it is aimed that the transmitter will generate a very narrow band of frequencies closely spaced in the electromagnetic spectrum, so that all of those wavelengths can travel at approximately equal speed. However, if the transmitter is generating a broad spectrum of light, then some light waves will travel faster because of higher frequencies, whereas the other waves will travel at a low speed because of longer wavelength. This will cause dispersion of the light signal. To avoid this thing, high-speed lasers are used to produce a very narrow spectral output. That is, the beam that is being generated by these lasers has only one kind of light in it. The second reason for dispersion is called modal dispersion. And this is what we have talked about when we discussed the modes of the fiber optic cable. Each mode is traveling a different path and hence a different length. Therefore, the light traveling in each mode will take a different time to reach the other end. The last reason for dispersion is called the waveguide dispersion. Although it is quite negligible, but it is still there. This minor amount of dispersion is because of the geometry of the fiber that is responsible for different velocities for each mode. Ideally, if the rays of light present in a beam are all of the same frequency, they should travel at the same velocity. But some modes might have a reduced velocity because of the geometry of the fiber. Now, based on everything which we have discussed about the construction and the way the light travels in the fiber optic cable, we can have three different forms of fiber optic cable. These three forms are dependent on the wavelength of the light that can travel inside the core and the mechanical geometry of the fiber. The first type is called the monomode or single mode. It is the thinnest fiber optic cable you can find. The second type is called multimode graded index fiber optic cable. It has a bit larger diameter than the single mode fiber optic cable. The last form is called the multi-mode step index fiber optic cable, and it is the largest diameter fiber optic cable you can find. As the name suggests, in the single mode fiber optic cable, only the zero mode will travel. Due to the fact that only one mode is traveling in the fiber optic cable, and that is the zero mode, which is the fastest mode, there will be no problem of dispersion of data. And hence the data carrying capability of this kind of fiber optic cable is the largest among all the types of fiber optic cables. In the multi-mode graded index fiber optic cable, the core has evenly distributed refractive index as you move from the center of the core to the edge of the core. This allows the light near the edge of the core to travel faster than the light traveling at the center of the core. Due to this, all modes reach the other end at approximately the same time, causing minimum dispersion. You can easily understand this thing, that if light that is bouncing from one edge to the other edge and is traveling forward will cover the largest distance, but as it is moving near the edges, it will move at a greater speed. Hence, the time taken by this mode will be similar to the time taken by the zero mode. And in the last type, the multi-mode step index fiber optic cable, which is the simplest fiber optic cable because of the fact that the whole core has a constant refractive index and there is no bending or speeding up of different modes. This kind of fiber optic cable is the cheapest and causes the largest amount of dispersion and hence has the lowest data carrying capability. Normally in practice, these kind of fiber optic cables are used for imaging and illumination, whereas graded index fiber optic cables and single mode fiber optic cables are used for data communication. As I have already said that the monomode fiber optic cable will only allow the zero mode to travel in the core. This is ensured by a number of factors, out of which the most important one is the wavelength cutoff value. This is the wavelength or the frequency of the light that is used with the monomode fiber optic cable. Apart from the wavelength, the core diameter and the numerical aperture, is also responsible for allowing only zero mode to travel through the core. If you will use a lower wavelength than the wavelength cutoff value, that is, the higher frequency light, then higher modes may also propagate through the monomode fiber optic cable, and this will kill the purpose altogether. So if there is only one mode traveling through the fiber optic cable, then there will be no model dispersion. Hence, pulses of light can be transmitted much closer in time. Because of their high data carrying capability, monomode fiber optic cables are used for long-range communication systems around the world. As far as the multi-mode graded index fiber optic cables are concerned, the first thing that you will notice is that they have a much larger core diameter, which will allow multiple modes to travel inside the core. Moreover, the refractive index will decrease gradually as you move from the center of the core to the edge of the core. This will allow the light traveling near the edge of the core to travel faster than the light moving at the center of the core. Therefore, different modes will take a curved path, and the modes which are traveling mostly near the edge of the core will travel faster, and the modes which are traveling near the center of the core will travel slower. So the slow moving modes will travel the shorter distance, whereas the fast moving modes will travel the larger distance, and they will reach the other end at approximately the same time. This will cause a considerable reduction in the model dispersion. Normally, these kind of fiber optic cables are used in local area networks. For example, any organization might have installed fiber optic cables to establish a network within its boundaries. Then they will be using a multi-mode graded index fiber optic cable. And for the last multi-mode step index fiber optic cable, the core has a uniform refractive index and the largest diameter. This allows maximum number of modes to travel and will cause the maximum dispersion as well. Therefore, if you want to transmit data using these kind of fiber optic cables, then because of the largest dispersion, the data transmission rate will be the lowest. Because of their high power carrying capacity and low data carrying capacity, these fiber optic cables are normally used for imaging or for illumination or even for transmission of high power laser light from one location to the other location in an industrial setup. As far as the fiber optic cables are concerned, the bandwidth is expressed in frequency dash distance units. Bandwidth represents the data carrying capacity of any fiber optic cable, and we know that it depends on the frequency of the signal and also in case of fiber optic cable how far that signal can be carried by the fiber. Therefore, typical units for bandwidth in case of fiber optics are megahertz-kilometer or gigahertz-kilometer. For example, a fiber with 400 megahertz-kilometer bandwidth can transmit 400 megahertz frequency signal at a distance of 1 kilometer. Or you can use it to transmit 20 megahertz frequency signal for 20 kilometers. If you want to transmit the signal even at a longer distance, then you have to reduce the frequency, that is the data carrying capability. Out of all the reasons, the primary reason for limit on the data carrying capacity of any fiber is the pulse broadening or the lengthening of light signal in time. And we have already talked about it that the main reason for this broadening is the modal dispersion and the chromatic dispersion. Typically, the single mode fiber optic cable will have a bandwidth around 100 gigahertz-kilometer, whereas the graded index fiber optic cable will have 500 megahertz-kilometer bandwidth for 1300 nanometer light waves, whereas for higher frequency light waves, the bandwidth drops to 160 megahertz-kilometer. As far as the step index fiber optic cable is concerned, it has the lowest bandwidth, and that is in the range of 20 megahertz-kilometer. This was everything that I have to discuss for fiber optic cables. I've covered the basic construction principles, different type of fiber optic cables, how light travels through the fiber optic cable, and what are the different aspects that favor or hinder the transmission of data transfer through the fiber optic cables. And at the end, I have also talked about different forms in which you can find a fiber optic cable and their practical uses and bandwidth they have to offer. I would like to end this video with the hope that you have understood the basics and the working principle of fiber optic cables to a reasonable extent. If you like our video, then hit the like button and subscribe to our channel. Thank you.